Just like we had our main definition of a derivative where we showed you where that came from using the slope of the tangent line, we have a main definition of an integral. All right. Now, technically what this is going to start off as is finding the exact area underneath the curve between the curve and the x-axis. You know, when that's curvy, if it's a straight edge, I can use geometry formulas, but the instant I get the curve involved, we need calculus in order to find that exact area. And just like the derivative started off as like a slope, and then it turned into rates of change and then velocities, accelerations, using it to find maxes and mins, the integral itself is going to have a lot of applications to it. It's basically an accumulator. It will accumulate and add up anything we want to add up. Right now, we're going to use it to add up areas of rectangles and find exact areas underneath that curve right there. So this is our main definition. So we're going to practice this long way, and then we're going to learn tons of shortcuts, exactly like when we did derivatives. We had our main definition, did tons of shortcuts right there. So let's go ahead and practice this thing. All right. Now, from a prior section, we had you using rectangles to find area, to estimate the area underneath that curve right there. And when you did the rectangles, you were using the width of the rectangle. Now we're going to do it in this general sense, and we're not going to find an estimated answer using just rectangles. We're going to find an exact answer of that area involving with the calculus involving the limit. So the delta x was the width of one of those rectangles. If you subtracted your integral and divide by how many rectangles you have, that gave you the width of each rectangle. And then this x sub k that we're going to call it is a plus k times delta x. So you're going to start it at your interval, and then you're going to go to like the first rectangle, your second rectangle, your third rectangle. And basically this is going to move you along your shape from your beginning end point to your end point right there. And it's going to take you across your shape and doing the areas of each rectangle right there. And then, so once you find your x of k, that's going to move you throughout the different rectangles. And then you're going to do f of x of k. So whatever you get for this, you're going to take it and you're going to plug it in for x into your function. And that's going to give you your height of the rectangles, right? And so this main definition, what it's doing, this is the delta x, that's the width of a rectangle. This is f of x of k, that's going to be the height of the rectangle. So when we do base times height, that gives you the area of one of those rectangles. The summation notation is going to add up each one of those areas of the rectangles. And then what calculus says is, it doesn't matter like if we have 30 rectangles or 50 rectangles. Let's talk about what this limit thing is going to do. So if we give you just a little picture here, if I use 10 rectangles and it goes above and below, see how that extra space that we're missing, or that extra space that we covered there? And then if you increase it to 30 rectangles, then you have a less extra space. You have more rectangles and less corners that you have extra. And then if you increase it to 50 rectangles, that's even like a better estimate, a better approximation. But see, right now, if I run my finger along this curve, it's going to be like, and it's going to be sharp, and I might hurt my finger a little bit if those edges are too sharp, right? And so what the integral is going to do, calculus says 50 rectangles, even 50 million rectangles isn't good enough. That's not going to be an exact answer. So in our formula for our main definition of the integral, the n stands for the number of rectangles, and you're going to do the limit as that number of rectangles approaching infinity. So we're going to slam an infinite amount of rectangles in that space. So then when I run my finger along those edges, it ain't going to go anymore. The integral, this limit notation is going to act like the sandpaper, and it's going to smooth off all those rough edges for us. And it's going to be the exact area underneath that curve right there. So it's just pretty powerful that the integral symbol contains all this stuff in it. So then when we're doing our shortcuts and stuff, we don't have to worry about all these details so much. But let's just practice this main definition, and we'll go from there. Basically, I'm going to go 2 examples. All right, I'm going to do a pretty basic one and then a little more involved one. So you can go to whatever part you need to rewatch or refresh anything, jump to any part of this video where you think that might help you. Okay, so all this stuff you're expected to know. And then in the middle of the problem, there's going to be some formulas that we're going to need that will always be given to you. So this you got to know, this you got to know, the process you got to know. And then in the middle of the problems, these formulas here, these ones you don't have to have memorized. These will be given to you, okay? So let's go ahead and let's get to it. So I have a function, give you an interval. This is my A, this is my B, and I want to find the exact area underneath that curve in between 0 and 5. So that's what we're going to find right now, and this is our main definition of our integral. So you need these 3 things always. So we're going to go to the side. We're going to go delta x is b minus a over n. So that's 5 over n. There's my delta x. And then the x sub k is always a plus k times delta x. So our a is equal to 0. So we're going to go 0 plus k times that delta x that we just calculated right there. And so that's going to give us 5k over n. And then what you need to do now is find f of x sub k, which means you need to take whatever you got for the x sub k, plug that in for all the x's into that original equation. So when I plug it in there and then I need to square it, I'll square the top and the bottom. We'll get 25k squared over n squared plus the 2. Remember to carry down that plus 2. So there's our f of x sub k. So we need to find those things right away. And then after you find them, we're ready to go to the formula. So we're going to say the exact area underneath that curve is going to be the limit as n approaches infinity of the summation from k equals 1 to n. And then we're going to go f of x sub k. So I'm going to take that, insert that right here. So I'm just plugging into the formula. There's my f of x sub k. And then you got to remember to times it by the delta x, which we calculated is a 5 over n. All right, so when we assess over this, we got to know all that stuff off the top of our head. And then I'm going to check that notation. We got to have that notation there perfectly, exactly like that. And then the whole rest of the problem, we're not going to need to rewrite that limit notation all the way to the whole thing, but we got to remember to take the limit at the end. Now, once I get to this point, I'm telling you, once I get to this point right here, I have a sense of relief there, because sometimes it gets a little messy over here. We got to do some legwork. But once I get to this point, I'm going to show you, I'm going to be very consistent. I'm going to do the same way, the same exact solving steps on every single one of these problems, whether it's an easy problem like this or whether it's a more involved problem like the second example I'm going to show you. I'm going to do the same exact thing, and I encourage you to develop that same consistency in order to solve these things the right way. So notice that this limit as n approaches infinity. I'm essentially going to ignore that until the very end of the problem. I'm going to eventually get all n's in my problem, then I can do my easy limit. And then right here, so this is what I'm always going to do. I'm going to take this 5 over n, this width, and I'm going to pull it out in front of this limit notation, this summation notation. The summation notation evolves in k's, and so you could pull out numbers, you could pull out n's. You just got to leave the k's in the problem there. Here's ultimately what we want to try to get. I want to try to get the summation of a number, or the summation of k, or the summation of k squared, or the summation of k cubed. That's eventually what I'm going to work into the problem right here. So I'm going to take this 5 over n, I'm going to pull it out in front, and I'm essentially taking this summation notation, I'm distributing it through the parentheses. So the 5 over n is going to be times everything. Now, what you're allowed to do is pull out any numbers and any n's in front of that limit, in front of that summation notation, because you got k's involved. Okay, so I'm trying to get the summation of a number, a k squared, or a k cubed. So right here, when I distribute this, I got the summation of this guy, but I'm allowed to pull out the number part in the n part. So I'm going to pull out the 25 over n squared, and then we have the summation of just that k squared part. And then we go plus, and I'm going to take the summation of the 2. So you have a number right there. You want the summation of a 2. So that's what I'm talking about. So you're going to distribute. You want to work in, at this point, either a number, a k squared, or a k, or a k cubed. That's what we're going to work into the problem right there. So you got the numbers and the n's. Those could come out in front. All right. And so now at this point, we're going to use our formulas now. Once you get these involved, there are these formulas here. You can kind of pause and jot those down. These will always be given to you. So as you're assessing that, well, I'll probably just kind of write those on the board or something like that, or have those up on your test already. But here's what we're going to use it convert it. When we have a number, a k squared, or a k cubed, we're going to convert it in terms of n. So if you have a number, it's just going to be that number times n. If you got a k, we're going to go n plus 1 divided by 2. So those are the formulas. You know, I got them memorized there. I think you'll probably have them memorized after you do a few of these problems, after you do this homework assignment. But those are the ones I'll always be given to you. Everything else that you're expected to know. So here's what I'm going to do. The 5 over n is just there. Now I'm going to carry down the 25 over n squared. And when I do the summation of k squared, I got this guy right here. I'm just going to replace it with that. That's what it's equal to. So we're going to replace that with n plus 1, 2n plus 1, all over 6. And then you're going to go plus the summation of a number. Now, anytime you have a number, it's really like you're adding up 2 plus 2 plus 2 plus 2 n number of times there. So whenever you have a number, it's just going to be c times n. And so that's all you're going to do here is just going to get a 2n when you have that number. And then this 5 over n is with both terms there, separated by that plus sign. So I'm going to take the 5 over n, I'm going to multiply it by this term here. I'm going to take the 5 over n, I'm going to multiply it by this term right here. Notice that we use those formulas to get rid of the k's. We have nothing but n's in the problem at this point. And then so if I go 5 times a 25, that's going to give me 125. Carry everything else down. And then here you have a 6n squared, times it by that extra n right there. So that's going to be a 6n cubed plus, when I take 5 over n times 2n, the n's cancel out, and you just have 10 that you're left with. All right, so once you use the formulas, get rid of the k's, get nothing but n's in the problem, and then distribute, make it look like this. Now what we're going to remember to carry down is the limit notation. So now I'm going to carry this down. I have nothing but n's in the problem. I'm going to do the limit as n approaches infinity of all of this stuff. Now, when you're approaching infinity, the highest degrees are the only thing that matter. Okay, so this is going back to the last section there where we're doing these easy limits. These are going to be real quick parts at the end of the problem there, because like infinity cubed, like a billion cubed is going to be so much more than just like, you know, like a billion, you know, so it's going to be, you're always going, when you're approaching infinity, you're always looking at the highest degree. So if you were to multiply this all out, you don't have to separate all these, you don't have to multiply everything out, but if you were to multiply it all out, you have 125 times 2, which is going to give us 250. You have n times n times n. So n cubed is your highest exponent, followed by a bunch of stuff that we do not care about. That's your highest degree on the top. And then you have a highest degree on the bottom is a 6n cubed. And then, so notice that the degrees are the same. Anytime those degrees are the same and you're doing a limit as n approaches infinity, it's just going to be those leading coefficients right there. So that portion is just going to be 250 over 6. And then whenever you do the limit of a number, says you're also doing a limit as n approaches infinity of the 10. Whenever you do the limit of a number, it's always equal to that number right there, because that's just a horizontal line. So no matter where you're at, your y's are approaching that number of 10 right there. So you got 256 over 10. And then so that's like 125 over 3 plus the 10, which is a 30 over 3. So this is going to give us 155 over 3. And remember what this represents. This represents the exact area underneath that curve, that x squared plus 2 curve, in between 0 and 5. So when that's curvy, that's when that calculus will give us that exact area right there. Now, a couple things. The first couple of assignments, the first couple of problems that you got to do, I think they might just kind of start you off in the middle and kind of have you practicing using the formulas a little bit and doing your limits right there. And there's no guarantee that the exponents are going to be the same on the top and the bottom. But the instant you start doing these problems like this, where you're finding the area and they give you that function and you're doing everything from scratch like this, when you get down to this point, those degrees should be the same on the top and the bottom. So if you have an n to the third and an n to the fourth, that's not okay. You messed something up. So you might go back and double check. You probably made a mistake when you're doing your f of x of k. Maybe you forgot your delta x to tag that on. But when you're doing these from scratch, those degrees should be the same on the top and the bottom. If not, you need to go back and kind of fix that. Like I said, the first few homework problems that you have, they might not be the same. It might be okay to have an n cubed over an n squared or an n cubed over n to the fourth. And, you know, if its degree at the bottom is larger, then that's going to be 0, because they're just kind of making up and having you practicing the algebra a little bit. But the instant you start doing the area problems and doing everything from your own from scratch, those should be the same right there. So I'm going to do one more example and just a little bit more of an involved problem just with the algebra, find the f of x of k. But the process is essentially going to work out the same way here. And so this time I'm going to give you this equation, and then the a is 2, and then the b is going to be 5. So graphically, what we're doing, if you graph that function, and then you're finding the area in between 2 and 5, and notice this whole graph is above the x-axis, so you're finding the area between the curve and the x-axis there, and that's going to give us the exact answer. So here's our a, here's our b, and anytime your a is something other than 0, you're going to have something a little bit more involved, depending on what that equation is, depending on what that exponent is. All right, so let's just do one more problem, and then we're done. All right. All right, so this has everything in. You can handle this stuff. You're going to be able to handle all the problems that we throw at you like this. All right, so delta x is just b minus a over n. So it's going to be 3 over n for our width. X sub k is going to be a plus k times delta x. So you're going to go 2 plus k times that. So that's 2 plus 3k over n. There's our x sub k. And then you need to take that, plug it in for all the x's into that original function there. So we're going to go 4 times this thing cubed. And notice, since you have a binomial cube, that's automatically making this problem a little bit more complicated. If that a was equal to 0, this would be such an easier problem there. So I just want to show you like the hardest that these will kind of get. So it will be good for everything. Now, what I strongly suggest you do not go straight to this formula unless this f of x sub k is simplified. There was nothing else I needed to do with that, so I went straight to the formula. If you have other things that you need to do, do your legwork right here. And then when we plug it into the formula, it's going to be the same level of difficulty every single time. So if you need to multiply this stuff out, which we do, multiply it all out right here, simplify it, and then we'll plug the simplified version into our actual formula. So the 4 I'm not going to worry about. I'm just going to essentially carry that down. Let's review the binomial expansion formula and the shortcut to cubing something. So what you do is you take this first thing and you increase the you decrease the exponent. So it'll be like 2 cubed and then 2 squared, 2 to the first, and then like none of them, all right? And then you'll take the second thing, which is your 3k over n, and you increase that exponent. So you go to the 0 power, so none of them, and then you're gonna go 3k over n to the first, you're gonna go 3k over n to the second, and then your very last thing all by itself will be a 3k over n to the third, just like that. And when you cube something, you need to remember your coefficients from your Pascal's triangle. Binomial expansion formula is the 1, 3, 3, 1. I would just have the cubed 1 down to 1, 3, 3, 1. You could draw your Pascal's triangle if you needed to raise some to the 4th power, but typically you just need to square stuff and cube stuff there. And then you simplify this right here. So this will give us an 8. This will be 4 times 3 times 3, so you're going to get a 36k over n. This will be a 3 squared, which is 9 times that 6 right there, so that'll give us 54k squared over n squared. And then you're going to cube it, so you're going to get a 27k cubed over n cubed. And then remember to carry down this 4. I'm not going to distribute that 4 because that 4 we're going to end up pulling out anyway. So if you just distribute, you're just unnecessarily making those numbers too large, and it's just going to make that worse than it has to be right there. So this is what I mean. You want to do that legwork right there. If you need to cube something or square something or multiply anything out, do the legwork right there, and then we'll take this simplified version of f of x sub k, and we're going to plug that into our actual formula. So let's go ahead and I'll zoom out a little bit because this problem is a little bit lengthier. All right, so if I use my main definition of my integral, the exact area underneath that curve, we're going to write that perfectly with the notation. We're going to do limit as n approaches infinity of the summation from k equals 1 to n. And it's f of x sub k times delta x. So this is our f of x sub k. We're going to insert that in there. And then we're going to multiply that by our delta x, which is the 3 over n. So that's the thing that's got to be perfect there with that exact notation, exactly the way it is. And then when we simplify it, we don't need to keep being so technical with that there. So just have it in your first step. And then this process, I'm going to do the same exact process as I did on the last problem there. So I please encourage you to develop that consistency with it, and you're going to get all these right. I think these are kind of fun once you practice a couple of them and you just get those right. It's going to be good there. All right. So you're going to take now the 4 and the 3 over n. We're going to pull it out in front of the summation notation. So that's going to leave us with the 12 over n. And then I'm going to do a couple steps all at once. I'm going to take the summation notation and I'm going to distribute it through the 4 things in that parentheses. And at the same time, I'm going to try to work in a number, a k squared, or a k cubed. So you could pull out like the 36 over n. You could pull out the 54 over n squared. You could pull out the number and that n squared. So if I distribute that summation notation, if I get the summation of 8, that's good. That's the summation of a number. I want that. And then we're going to go plus the summation of this 36k over n. So I'm allowed to pull out the 36 over n in front of that summation notation, but then we have the summation of k, because k's are variable once you have that like that. So you can't pull out those k's at all. And then same thing, we can pull out the 54 over n squared, got the summation of k squared, and I'm allowed to pull out the 27 over n cubed, leave that with the summation of k cubed. And that's why I chose this example for the notes there, because I kept saying, hey, you want to work in a number, a k squared, and a k cubed. We have all 4 of those all in this one problem right here. So we're going to carry down the 12 over n. And now's the point where we're going to have, if I'm doing a test, we'll have these written on the board for you there. You can kind of check these in your notes. Now we're going to use all of these forms, all 4 of them we're going to use. So I got the summation of 8. That's just going to be 8n. And then we have the 36 over n, and now I have the summation of k, which is going to be our n plus 1 all over 2. All right, and then you got the 54 over n squared, and then when you got the summation of k squared, we're using this one, which is this guy right here, which is our n plus 1, 2n plus 1 all over 6. And then you got your 27 over n cubed, and then that's going to be the summation of k cubed, which is this formula right here. So that just allows us to convert it from the k's to the n's. You actually proved, the nice thing is you actually proved every single one of these formulas in your honors pre-cal days last year when you did mathematical induction. You proved every single one of these right there. So that's pretty nice. And now we just kind of get to use them now. And this is all over 4. So once you use those formulas, got rid of all the k's, you got nothing but n's in the problem. And now I'm going to take this 12 over n, because this 12 over n is in front of all of that stuff. So I got 1, 2, 3, 4 terms. I'm going to take the 12 over n. I'm going to distribute that to all 4 terms that we have inside that parentheses. And I'm going to do a couple things at once here. So I'm going to distribute that. I'm going to remember this is the point where I have nothing but n's in the problem. We're going to have the limit as n approaches infinity. And at this point, I'm going to check, make sure the degrees are the same on the top and the bottom. And I'm just going to worry about the highest degree. So if I take 12 times 8, 12 over n times 8, and the n's are going to cancel. So this 12 times 8 is just a number. It's just going to be 96. All right, here's what I'm going to do. I'm going to go 12 times the 36. That's going to give me 432. And then you have n times n. So I'm just focusing on the highest degrees. You have n squared followed by a bunch of crap you don't care about. And then on the bottom, you have 2n, but then you times it by this n right here. So 2n times n, you actually have 2n squared. And then that is the only degree on the bottom there. And now I have the same degree on the top and the bottom. So let's do the same thing here. Now you got to be careful because of this 2 right here. Very common mistake. Students forget about this 2. So you're going to take 12 times the 54, but then you're going to times it by that 2 as well. So 12 times the 54 will be 648, times it by the 2, that'll give us 1296. So you don't have to multiply all that stuff out, but if you did multiply it all out, that would be the leading coefficient. You have n times n times n, you got n cubed, followed by a bunch of crap you don't care about. And on the bottom, you have 6n squared, times it by that n, so you do have 6n cubed in the denominator. And in this part here, you're going to take 12 times that 27. That's going to give us 324. You have n squared times another n squared. So you got n to the 4th divided by 4. And you got n cubed times that n to the 4th. So notice I got the same degree on the top and the bottom. And when I'm doing the limit as n approaches infinity, the limit of a number is just that number. And when you are approaching infinity, if those degrees are the same on the top and the bottom, your limit answers are just going to be those leading coefficients. So 432 divided by 2 will give us a 216. 1296 divided by the 6 will give us another 216. And then 324 over 4 is going to give us an 81. So we're going to get 609 for our final answer. Boom. And then what we'll learn in the future is just shortcuts for that, and then show you how this number connects to some of our shortcuts in the future there. But please practice that main definition. We're going to need to do that. That'll be big points for us. And then we'll use the shortcuts the rest of the way.